Hello and welcome to BioRules video lessons. Now that you have studied evolution and genetics, we are going to take a look on an interesting calculation that can be done to try to find out frequency of alleles. It's the Hardy Weinberg principles. The Hardy Weinberg principle, or the Hardy Weinberg equilibrium, says that a population that is in equilibrium, that's not evolving, will have a certain proportion between their alleles in a certain frequency. And the proportion between the one allele and the alternative allele, so the dominant and the recessive, and also the frequency of the homozygote dominant, the heterozygote, and the homozygote recessive, they are kind of stable in a population that's not evolving. Why is that important for us? Because if we calculate the frequency of the dominant, in this case here the big A, and we name it as P for our purpose here, and if we have the frequency of the recessive, here that we're going to call it Q, we can use two formulas. This is the Hardy Weinberg formula that says that P squared plus 2PQ plus Q squared equals 1. That means that the square of the frequency of the allele capital A plus 2 times the frequency of the allele capital A times capital small caps A plus the frequency, the square of the frequency of the small caps A, the recessive, equals 1. And so here, the frequency of big A actually, ultimately, no, that one is the frequency of the big A small a, the heterozygote, which will have the same phenotype, and the frequency of the homozygote recessive that will have a different phenotype. So if we add those over there, that should be 1. So this is the Hardy Weinberg principle. Okay? How is that useful for us? If we have a frequency of P, so the frequency of the allele big A, 0.3, then the frequency of Q should be 0.7, because P plus Q should be equal 1, because we only have those two alleles into this example here. So P squared would be 0.09, so 9%, because 0.3 or 30% is the frequency of the P squared 0.09, 9% of big A. So the Q squared should be 0.7 squared, so in this case here 0.49. 49%. And the heterozygotes, 2PQ should be 2 times 0.3 times 0.7, which equals 0.42. That means that the heterozygotes, 42%, are going to be the number of heterozygotes in the population. That's the idea of the Hardy Weinberg principle. How that can be helpful for us? Let's get an example, a real one. The RH, or the rhesus blood type, positive or negative in the United Kingdom, is about 95% positives. No, that one is going to be big D or big D small d, because the D is the one that determines that you have the protein D, the protein RH. So 95% is going to be one of those two possibilities, or the homozygote dominant or the heterozygote. That means that the negative is the remaining 5%. So the negative is going to be small d. So if you have those values over there, we already should be able to find the P in the Q, because P squared plus 2PQ plus Q squared equals 1. Q squared, the number of small d is 0.05. So what's the number of G? The number of Q, the small d, is the square root of that number, which is 0.224. So the frequency of the allele Q, or the small d, is about 22%. Okay, so that is the one. And of course, the P is going to be 1 minus that, so it's about 77.6%. Okay, that's the D. The question now is that how many people are positives in UK but are heterozygotes? So the number of positives homozygotes is going to be P squared. So 0.602, so about 60%. The number of heterozygotes we already knew, the homozygote recessives we already knew, it was 5%, 0.05. But now the number of homozygote the number of heterozygotes is going to be 2pq, so 0.348. So 34.8% of the population in the UK are heterozygote for blood type. This is how useful this is. Okay, and for you to use the Hardy Weinberg principle, it has a certain assumptions to be followed. One, no natural selection should be acting, so no mutation nor migration should be happening. Okay, we should have an infinite population, and we should have no sexual selection, so there should be random mating. Of course, in real populations, this is not going to be possible because natural selection is going to be acting. There is going to be a certain level of mutation or migration. The populations are never infinite, and the mating might not be random. But if we assume a population is fixed in a certain amount of time, and you say that that's not happening in that moment, then we can assume that the population is in the Hardy Weinberg equilibrium, like the blood type Rh in the United Kingdom. In a certain amount of time, in a very short time frame, no, there is no natural selection acting at that exact moment, no mutation, no migration. The population, we say it's big enough, so there is not going to have genetic drifting or other effects of small populations, and that people don't mate because of the blood type. So these are going to be the assumptions that will make possible for us to try to estimate how many are there that are heterozygote, how many are homozygote dominant, how many are homozygote recessive. And also, this can be useful because if you have two time frames, we can compare the frequencies in between these two time places to see if one of those four assumptions have been broken. So if we have different frequencies, so there was evolution. That means that maybe there was natural selection, maybe there was mutation or migration, or maybe the population was not infinite and something like genetic drift has happened, or maybe there's sexual selection, no non-random mating. So this is how it can be useful for us. Okay. So another thing that can be very helpful for us, if we plot those values in here, now where in the bottom we have the frequency of P. Now, when you have a very high frequency of P, that means you have a very low frequency of Q. And when we look at the formula of Hardy Weinberg, that will tell us that when a frequency of allele is very, very small, like the Q here, for example, when the frequency is very small, probably most of them are going to be located in the heterozygote. So here, for example, we have very small frequency of Q. So where are they located? There is a little bit in here, but most is going to be in the heterozygote. And here, almost no homozygote recessive, and most of them are going to be in the heterozygote. So that tells us that if something is very, very, very rare, most of them is going to be located in the heterozygote. That's another thing that we can do. Now, take your time, do a very few questions here about the Hardy Weinberg principle to see if you are nailing the idea. I see you in another class.